Hey everyone, welcome to the facility. If you're joining me for this explainer today, it probably means you're looking at a future in material science, and specifically a B.Tech in plastics technology. Now, I want you to completely forget everything you thought you knew about this industry. Today, I'm going to give you a tour of the clean, high-tech, and honestly incredibly innovative reality of modern plastics engineering. We're looking at a field that is literally engineering the future of our world, from medical clean rooms right up to aerospace composites. Let's dive in.
Here's our quick itinerary for today. We'll kick things off with a welcome to plastics engineering, look at the academic blueprint, walk through design to mass production, talk about engineering a sustainable future, explore career trajectories and salaries, and wrap up with how to master your craft.
All right, Section 1, welcome to plastics engineering. Let's move beyond that old dirty factory stereotype.
Now, right off the bat, look at how incredibly specialized our polymer focus is compared to, say, general mechanical engineering. Don't get me wrong, mechanical engineering is a fantastic, broad field focusing on general machine design and kinematics. But plastics technology, it's highly specialized. You aren't just learning how to bolt a machine together, you're diving into macromolecular chemistry, designing high-precision injection molds, and really understanding the thermal and mechanical properties of advanced polymers. And honestly, because you're so specialized, you can step directly into technical roles in the polymer sector with virtually zero onboarding time. Trust me, industry leaders absolutely love that.
Moving on to Section 2, the academic blueprint. Let's talk about building your foundation.
So your university journey evolves really naturally. After you get your basic engineering foundations out of the way in year 1, year 2 dives deep into polymer physics, chemistry, and the whole science of additives and compounding. Then, by year 3, you're literally stepping into the future with plastics processing and the integration of AI and machine learning. Think smart factories and computer-aided manufacturing. Finally, year 4 is where the magic happens. It all comes together with advanced sustainable polymer engineering, extended producer responsibility, and a massive capstone design project, usually right alongside an industrial internship. You're walking out the door with real, tangible experience. As a lead engineer, if there's one philosophy I want to hand down to you right now, it's this: precision design is the foundation of modern manufacturing. Look, preventing manufacturing waste starts on your computer screen, not on the assembly line. Your goal isn't just to make things, it's to model polymer behavior down to the micrometer, simulating flow and thermal dynamics so that when we finally cut a mold, it's absolutely perfect on the very first try. Because if a polymer shrinks by even a fraction of a millimeter after cooling, well, that's the difference between a flawless aerospace component and a really expensive piece of scrap.
Okay, Section 3, design to mass production. Let's take a quick walkthrough of the shop floor.
So here's what your day-to-day actually looks like. You'll guide a product through these 4 exact steps. It always begins with digital CAD simulation, designing the part and simulating that molten plastic flow. Step 2, prototyping, and hitting the material databases to pick the exact right resin. Maybe it needs high thermal stability, or maybe it has to be biocompatible for medical use. Step 3 is translating that digital design into a physical aluminum or steel mold using 5-axis CNC tooling. And finally, Step 4, moving that mold into an injection press for automated mass production, where robotic arms are picking and placing millions of identical, flawless components. Actually, fun fact for you, a single high-quality steel mold can pump out over 1 million individual parts before it ever needs replacing. Pretty crazy, right?
But hey, we aren't just running machines blindly in the dark anymore. We are fully in the era of Industry 4.0. We've got IoT sensors embedded directly into our molding machinery, gathering real-time data. We use artificial intelligence to monitor cycle times, pressure variations, temperature, the whole shebang. This data-driven approach lets us optimize our efficiency and actually reduce manufacturing waste by up to 30%. Remember, in this job, you aren't just an operator, you are an optimizer.
Section 4, engineering a sustainable future. Let's talk about healing the planet.
The landscape is already shifting dramatically. Just look at this breakdown. Bioplastics, which are derived from renewable sources like starches, plant oils, and cellulose, already make up nearly 20% of the global plastics market. That's a fifth of the market. We are completely revolutionizing our feedstocks. You could literally be designing sustainable, compostable packaging materials that naturally decompose, fundamentally undercutting the carbon footprint of traditional manufacturing.
And these are the kinds of innovations you'll be working with every single day. We aren't just sorting trash anymore, folks. Chemical recycling actually breaks mixed plastics back down into their raw catalytic components. It's a highly efficient closed-loop system.
We're also using microbial degradation, where we literally use specialized microorganisms and enzymes to eat away and break down synthetic polymers. This is where high-level biotechnology meets mechanical engineering, and it's absolutely fascinating.
Thanks to these technologies, and specifically using AI and machine learning to sort plastics, we're looking at a massive projected leap in global recycling rates. We're talking a jump from 20% in 2020 to an estimated 35% by 2026. As an engineer, you are the one designing these products to be recyclable from day one, making sure they fit seamlessly into this brand new circular economy.
All right, Section 5, Career Trajectories and Salaries. Let's talk numbers because I know you're wondering.
Let's look at the domestic market in India first. As a fresh graduate stepping in as a process engineer or a mold designer, you're looking at a solid starting salary between 4 to 6 lakhs per annum. But check out the growth trajectory here. With just 5 years of solid experience under your belt, optimizing cycles, designing high-precision tooling, that jumps up to 8 to 14 LPA. And if you lean more into the chemistry side, as an R&D scientist formulating new bioplastics, you could be looking at 10 to 15 LPA very quickly.
Now, let's expand your horizons a bit, because your skills are in demand all over the globe. In the US, an entry-level process engineer starts somewhere between $75,000 and $85,000 a year, with R&D scientists easily crossing that $100,000 mark. And in the Middle East, in places like the UAE, starting packages for specialized plastics engineers are incredibly competitive, often kicking off at over 156,000 dirhams. The demand for this specialization is literally global.
And if you need hard proof of that demand, look no further than this massive number right here. 80%. Top specialized institutes like CPET consistently see placement rates of 80% or higher. Why? Well, the polymer sector is expanding rapidly, and there just aren't enough specialized engineers entering the market to fill the void. When you graduate with this degree, recruiters are going to come looking for you.
I also want to quickly reassure you that getting a plastics degree doesn't pigeonhole you into one single industry. Your skills are needed everywhere. You could be designing lightweight, thermal-resistant battery housings for electric vehicles. You might be formulating carbon fiber reinforced composites for aerospace radomes. Or you could be standing in a clean room designing sterile, biocompatible heart valves for the medical device industry. The versatility here is just unmatched.
Finally, Section 6, Master Your Craft. Let me give you some insider advice, straight from a mentor's perspective.
Here are the actual secrets to becoming a top-tier plastics engineer. First, don't guess. Utilize those CAD material databases early on to select the exact right resin for the job. Second, master your structural elements. You need to learn how to use ribs and bosses effectively without creating ugly sink marks on your cosmetic surfaces. Third, tackle the hard stuff. Learn to manage complex geometries and undercuts using side actions and lifters. And honestly, most importantly, get your hands dirty. Seek out low-cost injection molding machines, cut your own aluminum molds, and run physical trials. That hands-on experience is exactly what will make you indispensable on day one.
So I'm going to leave you with this final thought. The whole world relies on materials that are lightweight, durable, and highly adaptive. The industry desperately needs optimizers, innovators, and sustainability champions. We have the data, we have the technology, and we definitely have the career pathways waiting for you. So what do you say? Are you ready to step up, enroll in B.Tech plastics technology, and engineer the sustainable materials of tomorrow? Because let's face it, the future isn't just going to design itself.